All right, buckle up, everyone. We'll go deep on acceleration today.
Sounds exciting.
Yeah, should be fun. We got a ton of physics notes, even some course specs someone sent over. Looks like they're really getting into how things move.
Yeah, classic physics stuff.
Definitely. So no better time than now to break it all down, right? Even if you're not, a physics whiz.
Absolutely. We'll keep things clear, I promise.
I like that. I like that. So let's start simple. What is acceleration, really? Most people think it's just like going faster.
Right, like hitting the gas pedal. But it's actually more about how the velocity changes over time.
Hmm. How it changes. Okay. So is slowing down acceleration too, then?
It is. Slowing down, speeding up, or even just changing direction, that's all acceleration.
Yeah, my mind is a little blown right now. So braking is acceleration.
You got it. We call that negative acceleration or deceleration. Think about a car coming to a stop at a red light. Its velocity is decreasing, so it's accelerating, but in the opposite direction, it's moving.
So it's not just about speed then, but which way something's going to
Hmm.
and how quickly that's changing.
Exactly. Both velocity and acceleration are what we call vector quantities. They have both a magnitude, which is the speed, and a direction.
Gotcha. So a car speeding up going north is different from a car speeding up going south, even if they're like changing speed at the same rate.
Precisely. Direction matters.
Okay, that makes sense. Now, I've got this formula for acceleration here in my notes, and honestly, it's a little intimidating.
Yeah, I get that. It's a VUT.
Okay, bring that down for me. What's all that stand for?
So A, that's acceleration, what we're trying to find.
Yeah.
V is the final velocity of the object. U is its initial velocity. And T is the time it takes for that change to happen.
Okay, so if we know how fast something starts going, how fast it ends up going, and how long it took, we can just plug those numbers in.
Exactly. That'll give you the acceleration.
Cool, cool. Like, say, with Usain Bolt. If we know his starting velocity, his final velocity at the finish line, and his record-breaking time, we could calculate his acceleration during that race.
That's a great example. You could totally do that.
That'd be a cool calculation.
Yeah.
But what about stuff that isn't, actively being pushed or anything, like a ball just dropping to the ground? Is that accelerating too?
That's where it gets really interesting. Even a simple falling object is accelerating, and that's because of gravity. The Earth is constantly pulling it down, and that force makes it speed up as it falls.
So gravity's like a built-in accelerator then.
You could say that, and the longer it falls, the faster it gets.
Okay, makes sense.
Yeah.
So we've got the concept, we've got the formula, but how do they actually measure this stuff? Especially with things moving fast, like a falling ball?
Oh, they don't just eyeball it.
Right, right. So what do they do?
Well, there's this classic experiment with a ramp, a cart, and these things called light gates.
Light gate sounds fancy. What are those?
They're like super accurate timers that use beams of light. You attach a mask to the cart, which is basically a card with a certain length. And as that cart rolls down the ramp, the mask passes through each light gate, breaking the beam. And the gate records how long that interruption lasts.
So by timing how long it takes the mask to pass through, you figure out how fast the cart was moving at those 2 points.
Exactly. We know the distance between the gates and the time it took to travel between them, so we can calculate both the initial and final velocity of the cart.
And then once you have those velocities and the time, you just plug it back into that acceleration formula.
Exactly. It all comes together. And by carefully setting up the experiment, you can determine the acceleration of the cart as it goes down the ramp.
Cool. Makes sense. It's like
Yeah.
all coming together now,
Yeah,
Makes you look at the world a little differently.
it definitely does.
So I'm guessing there's even more ways to measure acceleration though, right? Like even more precise methods.
You're definitely right about that. There's a technique called the double mask method. That one's even more precise.
Double mask method. Sounds interesting, but maybe let's let all this sink in for a second first.
Good idea. We've covered a lot already. All right, so we've talked about how physicists actually measure acceleration in the lab, all those experiments and stuff.
Yeah, like gates, ramps, it's pretty cool.
It is, but, not all of us are setting up physics experiments at home.
Definitely not. So why does acceleration matter in our everyday lives? Why should we care about this stuff?
Well, think about it. Acceleration's happening all around us, all the time.
Is it?
Yeah, every time you speed up, slow down, turn a corner, you're experiencing acceleration.
Oh, right, right. Like when I'm in a car and it takes off from a stoplight, I feel that pushback in my seat. That's acceleration.
Exactly. Or when that same car slams on the brakes and you feel yourself pulled forward, that's deceleration, which is, just another type of acceleration.
Ah, okay. So it's not just theoretical, it actually affects us.
Yeah, it can even affect our safety. Like wearing a seatbelt helps protect you from those sudden changes in motion.
Makes sense. And it's not just cars.
Right. Think about amusement park rides. All those drops and twists and turns, that's all about manipulating acceleration to create those feelings of excitement.
Oh yeah, roller coasters. It all comes back to physics.
It really does. But okay, let's go back to those forces we were talking about earlier. What causes acceleration in the first place? I think your notes mention Newton's laws.
Oh yeah, those laws always sound so, I don't know, serious.
They are fundamental, but they're not that complicated, really. Newton's second law, the one that's most relevant to our discussion, it basically says that acceleration is directly proportional to the force you apply to something and inversely proportional to its mass.
So the harder you push something, the faster it accelerates. And the heavier something is, the slower it accelerates under the same force. That seems kind of obvious now that you say it.
It's pretty intuitive, yeah.
Okay, but how does that apply to, like, a rocket launching into space? That's got to be a lot of force.
It is. A rocket needs a huge amount of force to overcome Earth's gravity and accelerate upwards. Its engines generate that force by expelling hot gases downwards, which, according to Newton's third law, creates an equal and opposite force pushing the rocket upwards.
So it's like a controlled explosion.
Basically. But at the same time, you have gravity pulling it back down.
Right, right.
So the rocket has to have enough force to not only fight gravity, but also to keep accelerating upwards.
Wow, okay.
And as it burns fuel and gets lighter, its mass decreases, which actually makes it easier to accelerate further.
So it's like a constant balancing act.
Exactly, between the force of the engines, the pull of gravity, and the changing mass of the rocket.
Pretty crazy. But what about something a little more down to earth, like literally? What about a skydiver?
Okay, so picture this. A skydiver jumps out of a plane. At first, they're accelerating downwards super fast because of gravity, just like that ball we talked about earlier.
That makes sense.
But as their speed increases, so does the air resistance. That's the force of the air pushing back up against them.
So it's like their body's acting as a parachute at first.
Exactly. And eventually, the force of that air resistance becomes equal to the force of gravity.
Oh, so they stop accelerating.
Right. They reach what we call terminal velocity. They're still falling, but they're not speeding up anymore.
It's like a balance point.
You got it. And this principle applies to anything moving through, air or water, whatever, whether it's a skydiver, a car on the highway, even a swimmer. There's always these forces affecting how fast it's accelerating.
This is wild. We've gone from carts on ramps to rockets to skydivers, and it all ties back to acceleration.
That's the beauty of physics. It helps you see the connections between, all these different things, the underlying principles.
I'm definitely seeing things differently now. Oh, one more question before we move on. We were talking about terminal velocity before, where the forces are balanced and acceleration stops. But can something have constant velocity without any forces on it at all?
That's where Newton's first law comes in. That law states that an object at rest stays at rest, and an object in motion stays in motion at the same velocity, unless acted upon by an outside force.
So if there were no forces, an object could just keep moving forever, in a straight line.
That's the idea. At least in a perfect scenario with no friction, which, doesn't really exist in the real world. There's always some kind of force acting, whether it's air resistance or friction between surfaces or gravity.
Right, right. So even if something seems like it's moving at a constant speed, there are always forces involved, even if they're balanced out. It's like this whole hidden world of physics happening all around us.
That's a great way to think about it. And the more we understand about those forces, the more we can understand about the world around us. But speaking of understanding, we still haven't talked about that double mask method for measuring acceleration. It's a pretty neat technique.
I'm all ears. Tell me more.
Okay, so remember how we were talking about those light gates earlier? So with the double mask method, we're still using light gates, but the mask is a bit different this time.
Oh, okay. How's it different?
Well, instead of just one section, it has three. Two taller sections on the outside and then a shorter section in the middle.
3 sections, okay?
Yeah, the two outer sections, those are the ones that actually start and stop the timer, like before.
Right, when they break the beam.
Exactly. But the middle section, that shorter one, it doesn't do anything to the timer.
So it passes through the light gate but doesn't trigger it.
Exactly. And by carefully measuring the widths of those sections and the time it takes for all three to pass through, we can actually figure out the instantaneous acceleration of the cart at a specific point.
Instantaneous, so not just the average acceleration over the whole ramp.
Right, it's like zooming in on a specific moment in time.
Wow, that's pretty impressive.
Ah.
But I have to ask, is there, like, a visual way to represent all this acceleration stuff, like something a little easier to grasp than just numbers and formulas?
There is. Have you ever heard of velocity time graphs?
Oh, yeah, I think I saw some of those in the notes. They kind of look like abstract art to me, though.
I can see that, but they're actually really useful for understanding acceleration.
Okay, tell me more.
So on a velocity time graph, time is on the x-axis and velocity is on the y-axis. And by plotting how an object's velocity changes over time, we can see its acceleration visually.
So instead of crunching numbers, we can just, like, see it happening.
Exactly. And the shape of the line on the graph, that tells us a lot about the motion.
Okay, so what does a straight upward sloping line mean?
That means the object is accelerating at a constant rate.
Like that cart going down the ramp. You're speeding up steadily, so that'd be a straight line going up.
Exactly. Now, what about a horizontal line? What do you think that means?
Let me think. Horizontal means the velocity isn't changing, right? So the acceleration must be zero.
You got it. The object is either at rest or moving at a constant velocity.
Okay, that makes sense. So straight line, constant acceleration. Horizontal line, zero acceleration. What about a curved line, though? What does that mean?
That means the acceleration itself is changing over time.
So it's not constant anymore.
Right. It could be increasing, decreasing, or even changing direction.
So it's like a series of mini accelerations all happening one after another.
That's a great way to think about it.
Okay, this is pretty cool.
Yeah.
But how does all this graph stuff actually help me in, real life?
Let's go back to that car example. Imagine you're approaching a red light and you start to brake. That deceleration would show up as a downward sloping line on a velocity time graph.
Okay, and the steeper the line, the faster I'm braking.
Exactly. Now imagine you see a pedestrian step out into the road in front of you. You have to brake even harder to stop in time.
Right, so that would be an even steeper line on the graph.
Exactly. So, by understanding these graphs, you can actually make better decisions about how to control your car, how to stay safe.
Wow, that's actually pretty helpful.
It is. And this stuff applies to all sorts of things, not just driving, designing airplanes, predicting the path of rockets, all kinds of stuff.
It's amazing how this one concept connects to so much,
It really is. And, as we wrap up here, we always like to leave you with something to think about.
Right, got to keep those brains working.
We've talked about how objects can have constant velocity with no forces acting on them, at least theoretically. But what about acceleration? Could something be accelerating if there are no forces on it at all?
Whoa, that's a good question. We have to ponder that one.
We'll leave you to explore that one on your own.
That's it for our deep dive into acceleration. Hope you enjoyed the ride, and until next time, keep exploring.